So last time I talked about magnetic fields. Magnetic fields are created by moving charged particles or currents. Magnets are very popular sources of magnetic field. Our earth itself produces magnetic field. All these magnetic fields which are produced, they are coming in some form or other. Currents are responsible for this magnetic field. And then if the magnetic field is there and you have charged particles there, moving charged particles, then this field will exert force on that particle. Or if there are currents, the magnetic field will produce force on that current. Interestingly, the force due to magnetic field is always perpendicular to the direction of the magnetic field. So magnetic field always deflects the particle. It will not increase or decrease the speed. It will not increase or decrease the kinetic energy. It will only deflect the particle. So if you have a magnetic field and you send some charged particle there with some velocity, the path will be deflected. So our first experiment will be on this phenomena, that if a charged particle goes in magnetic field, it is deflected and it goes along some kind of a curved path. You know the equation, force is equal to Q V cross B. If you have a charged particle Q moving with a velocity V placed in a magnetic field B, then the force on this particle because of this B is given by this equation. And if you send a charged particle perpendicular to a uniform magnetic field, then it goes in circle. That one can easily derive starting from here. So if you have a magnetic field, say magnetic field is going inside this board, so you have magnetic field shown by such crosses. These crosses are generally used for showing that the magnetic field is perpendicular to the surface and uniform. And then if you have some charged particle which is sent with some velocity, which is projected with some velocity in this uniform magnetic field, then the force acts on the particle V cross B. So here is B velocity and B is inside, so force will be in this direction. So it goes in a circular path. It's like this. It goes in a circular path. Okay. So our experiment will be demonstrating this fact that particles do go in circular path when they are placed in magnetic field and when they are given some velocity. So let me explain the setup, what kind of things we are going to use. So I have a Petri dish here and I have a aluminium ring, and I place this aluminium ring in this Petri dish at the periphery. Then I put some water in it. Then I put some salt, table salt. And there is a magnet. It's a ring magnet. The flat surfaces are the poles, this side and that side, and of course the poles are distributed. So poles are also on the curved surface, they are all distributed. One side is north, other side is south. So let me put this magnet below this Petri dish. I have an adapter which gives me some DC voltage, and I put one end of this adapter, I connect one end of the adapter to this aluminum ring, and the other end of this adapter is connected to this aluminum plate, which I will be placing at the middle. So, what will happen? The current will go to this aluminum ring, and then through this water in which I have dissolved the salt, it will come to this strip and then back to the adapter, and you see what happens when I connect it and switch it on. So, I am putting it here and then switching the power on. Just look at the water surface. You can see something is revolving. You can see some bubbles going in circular path. Some whitish things rotating clockwise direction. And if I put the power off, see that rotation has slowed down and now it is almost stopped. I put the power on again. And see the circular motion has started. Now let me reverse the magnet. So I put it off, take it down, reverse the magnet. So the polarities are different now. Put it back on the magnet and put the power on. Look at the water surface. It has again started rotating, but now it is going in anti-clockwise direction. So indeed this whole thing is because of the magnetic field. You can see the water mass is rotating in anti-clockwise direction. So let us understand how F equal to QV cross V is operating in this situation. Now, as you know, salt is an ionic compound. When we dissolve salt in water, the sodium plus and chlorine minus, they are separated, surrounded by water molecules. Water molecules are polar molecules, so they orient themselves particularly if you have ions in this mass. So you have positive particles and negative particles in this solution. When we are connecting this power, what we are doing is one end is connected to this aluminum strip, which is at the periphery of this petri dish. So we have some potential on this periphery. The other end of the power supply is connected to this strip, and that we put in the middle. So in this water in petri dish, At the periphery you have one potential and the center you have another potential. So you have a radial electric field. This radial electric field will try to accelerate the positive and negative charges, particles which are there in this solution. But then it's not a motion in free space. So although there are forces, it's not that the particles will accelerate to high velocities and so on. You have viscosity and all those other things, but they do start moving radially. And this magnet which is placed below the petri dish, it is giving roughly a vertical magnetic field. So magnetic field is vertical. The particles are there moving in radial direction because of the electric field started that way. And therefore you have magnetic force given by this q v cross b. So particles, velocity in radial direction to start with, and then the magnetic field vertical will provide the force to bend it. And therefore at the end of it, all things, viscosity of water and frictions and density and electric field and magnetic field will give rise to a steady circular motion that you have seen. If you invert the magnetic field direction is reversed, and therefore the direction of force is also reversed, q v cross b, and hence the force is in opposite direction, and from clockwise it becomes anti-clockwise, or from anti-clockwise it will become clockwise. Now we will be doing some experiments in which a magnetic field will be created by permanent magnet and the effect on a current will be seen. So I have here a small permanent magnet, this cylindrical shiny magnet, and I'll just put it on this board on which I have a battery and a wire, just a wire. One end of the wire is connected to the cell and another end is just hanging. I will be touching it to the other end of the battery, passing a current through it. It is going to be a high current because I have not added any extra resistance, only the resistance of the wire will be in the circuit. So I place this magnet near this loop here. This wire is just bent as a loop here and it looks like a head of a snake. So we generally call it a snake head experiment. Okay, so the magnet is here, it is producing a magnetic field and then I will be passing the current. So watch out for this snake head or this loop. See what it is doing. As I touch this end of the wire to the battery, this loop is going up, and when I remove it, it goes down. Okay. Now see the placing of this magnet. I will be changing this placing and I will bring this magnet right below the this portion of the loop. So let me put it here, and now let us see what happens. What do you observe? The lift is much less. Okay, now what happens if I reverse the magnet? The polarities are reversed. Let me reverse it and put it this way. And now I am touching this other end, and you see the force is downward, it attracts. Okay, so now let us understand why the motion of this loop depends on placing of this magnet. Slightly inside, the motion is very good and it goes up to a good extent. Slightly this side and the motion is very low. So why it is that? The first thing to understand is that if you have a magnet, then the magnetic field lines which come out of the north pole, they are not parallel, they bend, and they bend and go towards the other pole. Just to show, if you assume that this is the face of the magnet where the poles are there, so you have magnetic field lines coming out, but then they have to bend. So this will go like this will go like this will go like this, and so on. If you are right above this center, then the field line goes vertically, but if you are off that axis, then it will bend, and at certain position it will become horizontal and then go down. Here it will start like that, it will change direction, and certain place it will be horizontal and go down. It will start from here, will change the direction, at certain position it will become horizontal and then go down, and so on, like a fountain. Okay. So if I have put the magnet somewhere here, and the portion of the loop which is close to the magnet is right above the center, what kind of magnetic field it will feel? It will feel a vertical magnetic field. If it is north pole up, then the field will be vertically upward. And what is the direction of current? The battery positive is here, so the current starts here in this wire like this. There is a crossover here, so the current goes like this, and then goes like this, and then goes like this, and then goes into the negative of the battery. So if you look at the current here, then it is horizontal and it is going towards this direction. Current is going towards this direction, and the magnetic field is upward. And what is the basic formula for calculating force due to a magnetic field on a current carrying wire? The basic formula is the force on a small part of the wire is I, this is the current, and then dl, it is the direction in which the current is going, and the length dl on which you are calculating the force, cross product with the magnetic field vector. So here the dl vector in the direction of the current is in this direction, and the magnetic field vector is vertical, assuming that north pole is at the top, is going like this. What will be dl cross b? What is the direction of dl cross b? So you have dl here and b here, so dl cross b is in this direction. So the force is not lifting the loop up, and therefore the vertical motion of the loop is quite low. Of course, this analysis is for a perfect vertical field and all that. The directions are changing, so you have a small motion. And if the magnet is slightly inside, what happens? The field lines here become horizontal. Once again, assuming this is north, the field will be in this direction. So now if the field is in this direction and the dl is in this direction, what is dl cross b? This is dl, this is b, so dl cross b will be upward, and therefore the main force will be in upward direction and the loop will be moving up. So on the same lines, I have one more experiment which will also show how magnetic field direction changes close to the poles of the magnet. So for that I have a stand here, and these two aluminum rods are there. In fact, they are part of a coat hanger, normal coat hanger, and we fixed it here. Then we have an enameled wire, copper wire, and the two ends, the enamel has been removed from here, and in these stands you have these holes at the top. So the wires can go here in the hole, and once they are in place, this whole thing can move like a swing. So we normally call it a swing experiment because this wire can swing here. Now, we have a magnet, this time this is also cylindrical magnet, but flat disc type, height is small and radius is more. So, I can put it here near the base, okay, and then I have a power supply, DC power supply, and I can connect the two ends of the power supply to these coat hangers. So, the switch is off at this moment. Okay. So, what will happen when I put on the power? The current will go through this aluminum, will go through this swing, and then again through this aluminum rod back to the supply negative. All right. So, if you have this magnet, you have vertical magnetic field, and then in this lower part of the swing the current will be parallel to the wire. So, you will have a sidewise force. So, that sideways force will deflect this swing. So, let us see. Yes, it deflects away from me, governed by that F is equal to dF is equal to I dl cross B. Now, if I move this magnet and place it, let us say, somewhere here, and then see what happens when I put on the power. It comes towards me. At this position, it comes towards me, and at this position, it goes away from me. Same story, because of this magnet, the magnetic field here, let us say this is north pole. So, magnetic field here is upward, but then it goes, it becomes horizontal, and then it turns back. So, if this is upward here, this will become downward here, and hence if in this position, if the wire is experiencing an upward magnetic field, then in this position the wire is experiencing a downward magnetic field, and that is why these directions are different.